Hi, my name is Yamamoto and I would like to welcome you to the OOF2 tutorial. As you can see, I'm running OOF2 of the NanoHub website, which is exactly what you will be doing. Here I just launched the OOF tool and you can see that the welcome screen has popped up. In this window, in the very middle, we have the navigation menu. If you click on it, you will see all the different pages where you will be inputting different types of information to run your simulation. This menu has been arranged in a fairly logical order, and for the most part, you will be working your way down all these pages. For example, first you will load your microstructure, then you would process the image to try to bring out any relevant features that you might want. After that, you would assign the material properties to the different faces, then you would build your finite element mesh on top of that, assign the boundary conditions, and solve the mesh, and then you would analyze your data. So as you can see, it's fairly logical. To navigate in between all the windows, what you can do is click on this menu, or you can just use the arrows at the top. So now the first thing we need to do is load our microstructure. To do that, let's go to the microstructure menu and let's click on new image from file. This brings out another window, which is just our directory structure, and we can look for our microstructure, which in this case is called temp.tiff, and then spinodal.tiff, and we can assign the width of the microstructure, let's say 200 microns. Here you see that I'm using the e to the negative 6 notation, and I'm just going to leave the height as automatic, and OOF will figure out what the height of the microstructure is based on the aspect ratio of your image. Also, I want to point out that I'm using the 10 to the negative 6 notation because my standard units are meters. And that's something that I've chosen. I'm going to keep meters as my standard units, and all the units that I will be using through the simulation are going to be in units of meters. OOF does not have any built-in units, so being self-consistent on the order of magnitude that you use in your units is very important. So next let's click on OK, and you can see here that our microstructure has been loaded. To view the microstructure, we can just go to the Windows menu, then to Graphics, and click on New, and the graphics window will pop up. So as you can see, we have a two-phase microstructure that has undergone spinodal decomposition. Spinodal decomposition is a process by which a mixture of different materials tries to separate into two phases when there's a temperature change, for example. A particular example case where you would see this is in LEDs, let's say an indium nitride and gallium nitride LED. So let's assume that that's what our system is. Another thing that I want to point out here is that our microstructure is a little bit fuzzy. Let's try zooming in. You can see how the edges are not very well defined and they're a little pixelated. So let's go back to the main OOF window, and then on the next menu we have the image, and then here on the right you have the image modification tools. Let's click on it, and you can see that there's several types of image modification tools, like for example blur or dim, or you can add contrast, you can despeckle to reduce the noise. But what we're going to use is called threshold image, and let's just set threshold image to 5.7 to 0.57, and let's click on OK, and you can see how our image is turned into a simple black and white image, and the edges are more sharply resolved. They're still pixelated, and there's not much we can do about that as of now, but as you can see, there's no blurriness. We just have a simple binary image. So now that you've seen the image modification tools, let's go back to our microstructure menu, and let's create some pixel groups. As I said, we have two phases in our microstructure. The darker phase, let's say, is gallium nitride, and the lighter phase is going to be indium nitride. So we need to create a couple of pixel groups where OOF can recognize those two phases. So the pixel groups are just a collection of pixels, and that way OOF will recognize which pixels belong to which phase. So let's create the pixel groups by clicking here on New, and let's say our first pixel group is going to be indium nitride. We can click OK, and you can see that the pixel group has been created. Next we can click on New again, and let's call it gallium nitride. Okay, so now you see that we have two pixels group created, and you can see that each one of those have 0 pixels assigned to them. So now we need to assign pixels to to the pixel groups. To do this, we can go again to the graphics window. And here on the toolbox, you see that it says Viewer. If you click on it, we can go to the pixel selection pane. And then in Method, you have Point, which in this case, it selects a single pixel. And if we click on it, we can have different selection methods, like for example, a brush, which is going to be a circle or a square. We can set that up, and we can also set the radius, and then you can paint your selection. Then we have a rectangle, circle, or ellipse, all of them with which will select pixels in those particular shapes. Then we have color, which will select pixels based on the RGB color that we input or a grayscale value that we input. And we have burn also. Let's try doing burn first, just to show you what this tool does. And this one uses the local contrast in between the pixels to make the selection. So let's just click on the image, and let's click right here. And you can see that all the pixels that were of the similar shade, in this case, all those white pixels have been selected. So if we want to select all the lighter phase, which we said was the indium nitride, we can hold the Shift key down on the keyboard and click again. And you can see how I can select all the white phase. But since if we had a more complex microstructure, this would probably get tedious. So let's just clear our selection, and let's go back to Method. And this time, let's select Color. And then within here, in the color, we have this Delta RGB. Let's click on it also, and let's go to Delta Gray. And now we can just click somewhere, and you can see that all the all the white phase has been selected. And if we click on the dark phase or the black phase, you can see that all the black phase is selected. So again, let's clear a selection, and let's just click on the white area here. And all the white pixels in the image have been selected. And now that they have been selected, we can add those pixels to the indium nitride pixel group by clicking on the indium nitride pixel group and then clicking Add. And you can see that almost 7,600 pixels have been added to this group. If we go back to the graphics window, we can just clear a selection again. Let's click on the darker phase. You see how it was selected. And now we can add those pixels to the gallium nitride pixel group, and click on Add. And you can see that 7,000 pixels or so were added to that group. Next, we need to go to the materials property page to try to add the properties to the different phases that we have selected. So let's go there. Okay, so here in the materials page, you can see that on the left side you have all the properties that you can assign. On the very top you have color, and color is simply an identifier for OOF2. As you saw, we had two phases, so we can just assign two different colors to the different phases, and that's just going to be for us to identify the skeleton when we create it. And this will become more clear in the next few minutes. Next, we have all the mechanical properties, like for example the elasticity. If we click on it, you can see that we can input isotropic or anisotropic properties. And if we click on anisotropic, you can see that you can choose the crystal structure of your material. Also, you can input the stress-free strain of your sample or the force density. Also, you can input thermal properties, for example, the conductivity of your material, or whether your material is producing any type of heat here in heat source. And we also can input electric properties like the dielectric permittivity. Also, we have couplings, like for example, the coefficient of thermal expansion or piezoelectricity or pyroelectricity. And at the very bottom, you can see that we can do orientation maps, just in case you have, for example, a polycrystalline microstructure, and you have the orientation of each grain. You can see how the overall performance of your microstructure will change if the grains are oriented differently. So in the OOF2 universe, a material here is considered a collection of properties. And then, so what we're going to be doing is we're going to be creating the properties and assigning the properties to a particular material. And then this material is going to be assigned to pixels. So the first thing we need to do is create a material. So let's click here on New. And under Name, let's type indium nitride. And you can see that the indium nitride material has been created. let's go ahead and create the second one, which would be the gallium nitride material. And if I click on this box, you can see that I have the two materials that I have created. Let's go back to indium nitride. And here on color, the first thing I need to do is copy this property. And let's name it indium nitride color. You can see, we can click on OK. And you can see that the indium nitride color property has been created. If we click on parameterize, we can assign it a gray value in this case. So let's just say indium nitride is completely white, just to keep the same colors as we used in the microstructure. So let's click OK. And then we can assign this color property to the indium nitride material. So to do that, we just click here on Add Property to Material. And you can see that the color property, indium nitride color, has been added to our indium nitride material. The next thing we need to do is assign the mechanical properties for our material, and let's assign the elasticity, which we're just going to say it's isotropic. So let's copy this property, and we can say call it indium nitride modulus. Click OK, and you can see that it was created. Then we click on parameterize. There are several ways that you can input the elasticity of your material. Here you can see that you can input the tensor form, you can use the Lamé constants, you can use the Young's modulus and Poisson's ratio, or you can use the bulk and shear modulus. What we're going to do is use the Young's modulus and the Poisson's ratio. So let's set our Young's modulus for the indium nitride to be 150 gigapascals. So 150 e to the 9. And the Poisson's ratio, let's just leave it at 0.3. We can click on OK. And the next thing we need to do is add the property to the material. So we click here, and now you can see that all those two properties, the color and the elasticity, have been assigned to the indium nitride material. And now what we can do is assign this material, or this collection of properties, to a set of pixels. To do that, we click on Assign Material to Pixels, and you can see that this other menu pops up. And on pixels, you can do the selection, or you can select the pixel group that we created. That's why creating the pixel groups is useful, because it'll help you through the whole simulation. So let's click on the indium nitride pixel group and click OK. So now that material has been added to the indium nitride pixels. So now we need to assign the material properties for the gallium nitride phase. So let's switch materials, and you can see that our property box is empty. So let's go back here, and in color again, let's copy the color property, and let's call it gallium nitride color. Click OK. Now you can see that we have both of them, and let's click on parameterize, and let's just leave it as black. Click OK, and then we need to add the property to the material. And the next thing we need to do is copy the elasticity property, in this case gallium nitride modulus. Click on OK, and let's parameterize it. Let's go back to the Young's modulus and Poisson's ratio, and let's use 290 gigapascals for the Young's modulus, and the Poisson's ratio, let's just leave it as 0.3 also. Click on OK, and now we can add the property to the material. And the last step we need to do is assign the material to the pixels, and in this case we want to assign them to the gallium nitride pixel groups. We click on OK, and now our microstructure has material properties assigned to it. So the next thing we need to do is create a skeleton. To do this, we need to go to the skeleton page. Okay, to create a skeleton, we need to go to New, and we can assign the number of X elements and number of Y elements. Since our microstructure is fairly complex and there's a lot of detail, let's just start with a 30 by 30 skeleton. The next option we have is here you can see it's a quad skeleton, in which case we would have the elements in the skeleton would start as squares or rectangles, or we can choose a tri-skeleton. Since we have a lot of diagonal lines in the microstructure, let's choose a tri-skeleton. This brings out more options, more options of what we can choose. Here we can have the arrangement to be conservative, liberal, moderate, middling, or anarchic. What this means is that you're going to have the triangles in the skeleton are going to be created by dividing the squares or rectangles into two by a diagonal line. So you can choose the orientation of this diagonal line here, and let's just choose anarchic. Which one you choose is completely up to you. So we can click on OK, and if we go to the graphics window, you can see, well, here you can see that this skeleton was just created, and if we go to the graphics window, you can see that a mesh, or the skeleton, I'm sorry, has been laid over a microstructure. Let's here go to the toolbox and the viewer, and let's zoom in. Here you can see that we have several squares divided by the diagonal line into triangles. So let's go back, zoom back out. And here in the graphics window, you can also toggle between the different layers that you have. Here at the very bottom, if you click on the scroll bar on the side, or you can move this up a little bit, you can see that right now we have two layers. We have the image, which is the bitmap displayed method. So if we take that out, we don't see our microstructure anymore. And on top of that, we have the skeleton, which we can take in and out. Also, we want to see what OOF is considering each one of these elements to be. So let's go to the layers menu, so we can add a new layer. Let's click on new. Then on category, let's click on skeleton. And let's just leave all those there. Let's go to, in display methods, let's click on new. And instead of element edges, let's go to material color here. Click on OK. And you can see on the graphics window that now we have the different elements are colored now. If we zoom in, you can see how for example, these elements here are considered to be indium nitride, and these are gallium nitride. If we take the skeleton material display layer out, you can see our microstructure underneath. As you can see, we do not have a very good fit between the microstructure, which is displayed right now, and our skeleton. You can see that we have, lots of triangles, and it's just really not doing a very good job at matching our microstructure. So let's close this window. Okay, so let's go back to the skeleton menu, and here we have the skeleton modification tools. What these tools are going to do is try to get our skeleton to match our microstructure better. The first thing we are going to do is click here on method, and you have all these different methods by which you can modify the skeleton. Here, refine will add more elements to your microstructure. Anneal will start moving the nodes, and we'll be using the most relevant ones for our case in this case, which will be refine, anneal, merge triangles, and swap edges. The first one we're going to do is swap edges. Let's click on it, and what swap edges does is it will change the diagonal line in the squares, in the triangles, to try to minimize the energy. And by minimizing the energy, I mean trying to match the microstructure better. OOF2 has this concept of energy, and the lower the energy, the better the match of the skeleton to the microstructure. So we always want to try to minimize that energy. So let's click on OK. And if we go back to our window, we should have seen, yep, there you go. You saw how some of the elements changed, and we probably have a better match right now. So let's go back to the method, and now let's try annealing our microstructure. What anneal is going to do is it's going to move the nodes around, or the corners of the squares, to try to match our microstructure better. Here we have the concept of alpha. Right now it's set to 0.3, but let's change it to 0.7. The higher the alpha value, the more OOF is going to give importance to matching the matching the interfaces in our microstructure. And the lower the alpha value, the more evenly shaped our elements are going to be. Really skewed elements or really thin, really long elements are harder for the solver to solve. So we want to try to find an equilibrium between using elements that match our microstructure and elements that are not too oddly shaped. So here let's just set it to 0.7, and let's change the iterations to 25. Let's click on OK, and let's go back to the graphics window. Here you can see how some of the nodes are starting to move around. Let's zoom in a little more. Oops, let's zoom in a little to try to see that better. As you can see, we do not have perfect squares and perfect triangles anymore because the nodes are moving around to try to match the interfaces better. Here. And also we have the activity viewer window where we can see what the process, how much progress we have made on our steps. Here it says annealing skeleton, step 7 of 25. So let's bring that back over here. And let's just wait until OOF2 is done annealing our microstructure. Okay, so OOF2 is done annealing our microstructure. Let's zoom out to try to see what it looks like. And you can see that we have a much better fit than we used to before. Here we can take the material skeleton layer out, and you can see that, let's take the skeleton edges out also. And you can see that we have a much better fit, but still there's a little bit of jagged corners here. So what we need to do is increase the number of elements in our mesh to try to resolve all those features. Here, let's try doing the swap edges again, just to minimize the energy. It's a fast step, so it doesn't really matter. Okay. And then let's try to refine our microstructure. And then here you have the method, which is refine. And you can target all heterogeneous elements, or you can set it to target selected elements or elements in a particular group or phase or all elements. So here, let's just leave all the defaults on and click OK. And let's go back to our microstructure. There you go. And you can see that a lot more elements have been added to the microstructure, and we are resolving all the edges much better now. If we go back to the OOF2 window, we can do here again, let's do another quick swap edges. Click on OK. Here. Since we have a lot more elements, these steps are going to start taking longer and longer. Okay, and next let's anneal our microstructure again. Yeah, and let's just leave 25 iterations. Let's click OK, and let's watch it anneal. Okay, so our microstructure is done annealing now. If we go back to the graphics window, we can still see that we don't have such a great match to the microstructure. I mean, for the most part, we're resolving all the different microstructural features, but our edges are still a little bit jagged on our elements. So we still need to do a little bit more of processing of this skeleton. So the first thing we're going to do again is another swap edges step. And let's just click on OK. I think this swap edges step is really good at improving the fit of your microstructure without it taking too much time. Okay, so let's go back to the skeleton modification tools. And we're going to use a new tool called merge triangles. What merge triangles does is it'll merge two triangles into one quadrilateral element. The advantage of this is that bigger elements were, for example, let's go back to our graphics window. Let's put the skeleton back on. Oh, the skeleton edges, I'm sorry. And let's zoom in. Oops, the other way. Let's zoom in. You can see, for example, here that these two could be merged into one element, and what that would do is it would reduce the number of elements in your mesh, making it solve faster, and also it might improve the fit of your skeleton to the microstructure. So let's do the merge triangles, and let's just leave all the defaults again. Let's click on OK. Here you can see that right now number of quads says 0, and we have 6,282 triangular elements. After this tool is done processing, we can go back and you can see that now we have 482 quads, and the number of total elements in the microstructure has gone down a little, so that's probably good. Now let's go back to our graphics window and see what our microstructure is looking like. The first thing I see here is that we have this really long element here, and as I said earlier, long skinny elements are not very good for the solver because it's harder to make the matrix converge. So let's go back to the main OOF window, and let's do a little bit more of annealing. But this time, let's lower the alpha to 0.3. And what this is going to do, it is going to give more importance to the shape of the elements than actually matching the interfaces. I mean, an alpha of 0 would give you perfectly triangular elements, so like equilateral triangles or perfect squares. With a 0.3, we're still giving some importance to matching the interfaces, but we're going to try to get a better element shape also. And let's change the iterations to 50. And let's just let it go. Here you can see our activity window. Okay, so our skeleton is done annealing. Here, if we go to the graphics window, we can see that we have a fairly good match between the skeleton and the microstructure. Here we can take the different layers off, and we can see that we have a fairly good match. So the next thing we need to do is create our mesh. To do that, we can go to the FE mesh page, and here the difference is that the mesh has the mathematical and shape functions associated with the fields, while the skeleton doesn't. So what OOF is actually going to be solving is the mesh, not the skeleton. But to us, the skeleton and the mesh look exactly the same because they have the same node connectivity. So let's click on New, and this brings out this other window, and we have the mapping order and interpolation order, which right now is set to 1. That means that we're going to have linear equations in our elements. This is convenient because the code is going to solve faster, but that means that the element is going to have a single value through the whole element. Whereas if we set it to 2, then we'll be using a quadratic equation for the elements, and we can have slight variations in the field within the elements. And this is going to lead to more accurate calculations as well as smoother looking plots. Also, the drawback of using the quadratic equations is that it's going to take more computation time. But let's just go ahead and create our mesh using the quadratic equations that you see. And click OK. And here in mesh information, you can see that our mesh is going to appear in a second. There you go. You can see that our mesh has been created now. So the next thing we need to do is go to the next page, which is the fields page. And here we define which fields we want to input information for and which ones we want to solve. When we define a field, that means that the code is going to take it into account, and when you define it, you can input the values of it, like for example, the displacement, and when you activate it, the code is actually going to solve for that field. So since we're going to be putting a small tensile stress on our sample, we just want to click on the displacement field and define it, and we want to activate it also since we're going to be solving for it. The temperature and voltage fields, we can just leave them unchecked since we're not concerned about them. The last checkbox here is the in plane, and this means that the displacement, if we click on this box, the displacement would be in the plane. There wouldn't be any strains in the z direction. But since our microstructure is free to move in the z direction, which is in and out of the page or in and out of the screen, we can just leave this checkbox unchecked. Next, we need to go to the next page, which is the equations page. And here we're going to click on the plane stress and the force balance. Plane stress is used because we're going to have all the stresses in our microstructure are going to be in the plane of the page, and we're allowing the strains to move in the z direction. So the next thing we need to do is create our boundary conditions. So here we said we're going to apply a tensile stress on the microstructure. So what we're going to do is we're going to mechanically clamp the bottom of the microstructure, and then we're going to pull on the top. So to create a new boundary condition that represents these conditions, let's click on new. And on the displacement field, we have the x component. The force balance equation will have the x component. And on function, let's put 0 to represent no movement. And we're going to apply it to the bottom. So what this means is that the bottom of the microstructure cannot move in the x direction. We hit on apply, and you can see that our boundary condition was added. Then we can do the same for the y direction at the bottom of the microstructure. We hit apply, and as of now, our microstructure cannot move in the x or the y direction at the bottom of our microstructure. So the next thing we're going to do is apply a small strain, since this is a displacement field, to the top of our microstructure. So let's change it here to top, and on function, let's change it to 1 × 10⁻⁹, which is 1 nanometer, which, as you remember, our microstructure was 200 microns. So this is approximately 1/10,000% elongation in the vertical direction. So let's click apply, and now you can see that we have all our 3 boundary conditions. We can just click OK. Oh, hold on. Yeah, ignore that error. That basically assigned the same boundary condition twice. But now we have the 3 boundary conditions, and the next thing we need to do is go to the solver page. And here on the preconditioner, we're going to choose block, and then in plane is ILU. And this combination of the linear solver with the CG, or the conjugate gradient method, and the block preconditioner is one of the most stable ones for most calculations. So let's just use those, and we click on solve, and OOF is going to try to figure out what the stress field looks like. So let's click on solve. So now you can see that our mesh has been solved. You can see that the message under message here we have that the conjugate gradient converged. So so this is good because now we have an answer to our fields. If we had any conflicting boundary conditions, or maybe an unsymmetric matrix or anything like that, we would have gotten here an. Now that our mesh has converged, we want to visualize the results, or we want to visualize what for example, the stress field looks on our microstructure. To do that, let's go to the graphics window, and we need to add a new layer to all the ones that we already have. So let's click on layer, then new. Here in category, let's click on it, and let's select mesh. And you can see that in the object boxes, we have our microstructure, our skeleton, and our mesh. So then let's go to display methods, click on new, and at the very top, let's click on that box, and let's select field contour. And this is going to create a color map of the stresses in the microstructure. So let's click on it, and you can see that more options pop up. The second box here, you can click on it and you can see that you can plot either the field, the flux, the energy, or the strain. So let's go ahead and select flux, since we want to plot the hydrostatic stresses in our microstructure. And then here component, let's switch that to invariant. And on the invariant, let's select trace. And then let's just leave all these, the levels and number of bins as the default. And let's click OK. So right now the OOF2 is trying to draw the new layer. And let's just wait until it's done. Okay, so OOF is done drawing the field. Let's take the mesh edge display and the skeleton edge display off so that we can see the field a little bit better. Okay, you can see that our field looks somewhat very contrasty. You know, you have these areas of red and then this darker red, and there doesn't seem to be a smooth transition between all those areas. And that is because if you look at our scale bar, it only has 11 levels. So let's just click on the mesh layer and let's try to smooth out all these, all the features in there. So with a double click on that layer, the OOF graphics layer editor comes up. Then we click on the field contour one and we can click on edit. And then here on number of levels, instead of 11, which here on the side you can see that it's fairly not smooth, let's just choose 120. And on the number of bins, let's just lower it to 2. And now let's click OK, and let's hit on send to send the changes to the graphics window. And then again, now we need to wait until OOF draws it. Okay, so OOF is done drawing the stress field. And you can see that it looks much smoother, and also our scale bar does not look as blocky as it used to be. But because of the scale on it, you know, it goes from 4.5 times 10 to the 6 to negative 1.9 times 10 to the 5. It's kind of hard to really determine which areas of the microstructure are on tension and which are on compression. So let's try changing the magnitude on the scale bar here. So let's double click on the layer again to bring out the layer editor, and let's edit that one. Here on minimum, we can click on it, and it's no longer automatic. And since I've done this simulation before, I know that the negative 4 times 10 to the 6 will look pretty good. And then on the maximum, I'm going to put 4 times 10 to the 6. This way it's symmetric. You know, the maximum value and the minimum value are symmetric about 0. And let's click OK, and it's going to get redrawn. And now let's just wait again until OOF is done drawing. Okay, so OOF is done redrawing now, and you can see that most of the stresses on the sample are positive, which in this case will represent a tensile stress, which makes sense because we're stretching the microstructure vertically. Also, what we can see here is that if we take the results layer off, we can see that on the darker regions that are going vertically, like for example this area here, or these black regions here, we can see that the stresses are higher in those regions. Here, my mouse is over the black region right now. And when the stress layer comes up, you can see that that is a brighter shade of yellow. And this makes sense because the darker region has a higher Young's modulus, which means that it's bearing most of the, or more of the strain in the microstructure. So the next thing we need to do now, now that we can visualize our data, is try to analyze it. And to do that, we can output our data to files, for example, and we can go to Analysis. And here, we can go to Analysis. Okay, so OOF is done redrawing now, and you can see that most of the stresses on the sample are positive, which in this case will represent a tensile stress, which makes sense because we're stretching the microstructure vertically. Also, what we can see here is that if we take the results layer off, we can see that on the darker regions that are going vertically, like for example this area here, or these black regions here, we can see that the stresses are higher in those regions. Here, my mouse is over the black region right now. And when the stress layer comes up, you can see that that is a brighter shade of yellow. And this makes sense because the darker region has a higher Young's modulus, which means that it's bearing most of the, or more of the strain in the microstructure. So the next thing we need to do now, now that we can visualize our data, is try to analyze it. And to do that, we can output our data to files, for example, and we can go to Analysis. In the Analysis page, here at the top left, we have the output, which is the number that we want to be looking for. So since we plotted the stresses on the graphics window, let's go ahead and try to find the actual number for the stress. So let's click here on the field and go to Flux. Next, on Component, we can go to Invariant. If we keep scrolling down, we see that the flux is the stress, and then on the invariant, let's just trace. And all these options I just chose are the same ones that we plotted on the graphics window, so that's why I chose them. Next to the right, we have the domain. This is where OOF is going to be looking for that number. So, for example, we can do it in the entire mesh, which would just average the stress on all the microstructure. Or we can select, for example, a pixel group. So let's do that, and let's just do the indium nitride pixel group, for example. So this would output the stress just in the indium nitride phase. Next, we have sampling, in which case we have the grid points, which this would automatically lay a grid of 10 by 10, or you can set the number of X and Y points. If we click on it, we have also pixels. So let's just do that, and this would look at the stress value at every pixel inside the domain that we chose, which in this case was the indium nitride pixel group. Next, on the left, we have the operation. If we click on it, we can see that we have direct output, which would just show the value at each of the pixels in this case. This would be very messy, so let's just do the average. And next, we have the destination. Right now it's set to message window, but if you click on new, you can output it to a data file, and this would just create a simple text file. But since we're using the NanoHub, it's probably easiest to just use the message window to see the value for now. So let's cancel this, and let's leave it as the message window. And the message window is back here. So let's try moving that around so that we can see what happens. So next, we can just click on Go, and you can see that all our parameters were passed into OOF here. And next we should see the value of the stress in the indium nitride phase. There you go. You can see that we have a stress of approximately 0.9 MPa. And then let's change this to the gallium nitride phase. And let's leave all the other settings similar. And let's click on go. Again, you can see that all the parameters have been passed. And hopefully we will see a different stress. There you go. Here you can see that in the gallium nitride phase, we have a stress of approximately 1.24 MPa. Okay, so this concludes the OOF2 tutorial. I hope you found it useful, and I hope that you feel confident enough using this software to perform your own simulations. Thank you very much.